subtopic. All right. Okay. So what I will do first is there's actually a what do you call a surprise for you. Okay. We will start with just a video to get a little bit of revision or to make you remember back whatever that we have learned in the last lesson. Okay, and after the video ends, right, we will have a pop quiz, right? And this pop quiz, we won't be using what you call the website that we were using the other day, but what we will do is I will show you the question, all right, here in PowerPoint form, and each one of you will have to try to answer it on your own, all right? And I will give you about 10 minutes to answer the question. There will be 2 questions, and it is based on whatever that you have learned in the last lesson regarding the rate of reaction, all right? So I need you to answer so that we can then, after you have you are given 10 minutes to answer the question, all right? I would recommend that you try to answer it in a Word document, okay? Because then I will choose 2 persons to share your answers with the rest of the class, right? Now, from today's class onwards, right? So we have another 4 classes left, okay, from today onwards. So every class I will be asking question, all right? And I will, pick out one of you to give me the answer, right? So you have to be ready to share your answer on screen and also to give your answer, right? And what we will do is at the end of the week, the end of the lesson, which will be your last class is on the 25th of October, we will have a test, and I will also announce sort of like a winner for being the most active participant of the class, all right? Okay, so this is to encourage, I will give 2 persons, all right, 2 persons. Perhaps I might send some prize to Dr. Gallo to be given to 2 persons who's going to be actively participating in the next 5 weeks. Okay, all right, so that is my announcement, all right, and also the surprise. Okay, so make sure if your name is called out, you try your best to answer, and also please remember to always prepare your answers in a Word document that you can share to the group to discuss. All right, okay, so let's start with our video, right? So in the meantime, please prepare for the pop quiz that will be taking place right after the video. All right, okay, thank you.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those 2. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, so I hope that was a very interesting way to show the 5 different, the factors that will affect the rate of your chemical reaction, okay, that we learned last week, all right? So that's just a more fun way of putting it, all right? But as you can see, all those are the most important factors that you can actually play with in order to increase the rate of your reaction. Okay, so I hope now we are ready for the pop quiz. Okay, so let me share the quiz. Okay, and all of you, please get your Word document ready, and you'll be given 10 minutes to attempt, and I will choose the names. All right, I will call out 2 persons to share your answer. All right, okay. Okay, so you can start to try the question now. Okay, very simple. You can quickly do it. So just a little tips for question number 1. All right. In order to answer this question, you must remember that your rate is inversely proportionate to 1 over rate. Okay. Okay, 4 more minutes, quickly get it done. And get ready to to share your answers here. Okay, so I'm going to stop the sharing now, all right? And I'm going to choose two persons, okay, to share your answers with the class, all right? Okay, let's see. Can we have Putri Amalina Zarai? You can give the answer for the first question. And for the second question, can we have Muhammad Riwaldi? Okay, so Putri Amalia and Muhammad Riwaldi. Muhammad Riwaldi can give me the question for the answer for second question. All right. And Putri Amalina, can you share your answer for the first question? Can we have Putri Amalina? Let me see. Is Putri Amalina here? Are you here, Putri Amalina? No? Okay, if no, Putri Amalina is not here, we can have, how about Melinda? Melinda? Melinda is also not here today. Okay, if you answer the question, you can actually get a prize at the end of the semester, yeah? Can we have, or anyone else want to share your answer? Or maybe we can have Rivaldi. I can see Rivaldi is here, right? Maybe you can give us the answer for the first one. And I can choose another person for question number 2. Okay, Rivaldi, can we have the answer? Muhammad Rivaldi. Come on. Oh, I see Melinda is also here. So Melinda Nur TV, you can give us answer for the second question. Rivaldi, can we have the answer for the first question? Come on, guys.
Excuse me, Miss.
Yes.
Can I share my question?
Sure.
But I have but I've done number one.
Okay, Ken, sure. Your name, please?
My name is Kevin.
Kevin, okay.
Yeah.
Thank you, Kevin. You can share your screen and try to answer the question. Okay, Kevin, are you there?
Yes, doctor.
Can you share? Yeah.
Can you see my screen?
Mm-hmm.
Yeah. From here, I've closed the A and closed the B.
Mm-hmm.
Then I've concentration A for time. The concentration I is 155 second, and close the B from concentration B for time B that 75 second. Then I times it and find the equation that 15 concentration A equals 31 concentration B. Maybe that, doctor?
You are
Sorry if I'm
almost
wrong.
there. No, it's okay. Thank you. Thank you for trying, Kevin. All right.
Yes, doctor.
Okay, I will share the answer right now. Okay, there's just a slight bit mistake, but the first part is correct. All right, okay. Let me just share the first answer with you guys. All right. Okay. So, Kevin had almost got it right. All right. Okay. So the thing is, okay, rate of the reaction A. Okay, as we said, it is inversely proportionate, right, to the 1/time, right? If you remember from our previous lesson. Okay. So here it is given that your reaction A takes 2 minutes and 35 seconds, right? So 155 seconds. And the rate of reaction B will be 75 seconds. So it's 1/75. Okay. So when the question asks reaction A relative to B, it means that they want you to take RA divided by RB. Okay. So when you do that, you will get 0.484. Okay. So what do you call, Kevin? You are almost there, just that you did not give me the final value. Okay. Okay. Thank you. All right. So for the second question, the answer, can we have one more person? All right, before we start with our class today. All right, Melinda or anyone else wants to try? Kevin, thank you for trying. Okay, you will probably get something at the end of this semester if you keep up giving me good response. All right, can we have one more person? Thank you, Kevin. Can we have one more person for the second question? Also a very simple question, quickly, before we start our lesson for today. Come on. Where's Melinda or Rivaldi? You want to try? Or Valencia, Nopita? One more person, quickly. You guys have to answer, yeah, especially those who are registered students, okay? Maybe I should start minus marks when I call your name and you don't answer. I should start minus marks. Can we have one more, please? Melinda or Valencia? I can see you, so you can perhaps try to answer. Nobody? Maybe Rivaldi, can you answer? Okay.
Sir,
Yes.
can I answer? But
Yes, sure.
can I speak Indonesian language?
Sure, very surely can. Okay, you can always answer in Bahasa Indonesia, no problem. You can share your screen and answer now. Please introduce yourself, yeah?
I will introduce myself. My name is Muhammad Wahid Azami. Saya ingin menjelaskan jawaban nomor 2. Nah, di sini kan ditanyakan rate of average atau laju rata-rata. Nah, seperti rumusnya itu bahwa laju rata-rata itu perubahan mol dibagi dengan perubahan waktunya. Nah, di sini kan perubahan molnya, mol awalnya 0,300 dan juga dikurangi oleh mol keduanya atau jadi 0,292. Nah, hasilnya adalah 0,008 dibagi dengan 120 waktu setelahnya 120 detik dan juga dikurangi waktu sebelumnya itu 0 detik. Jadi 0,008 dibagi dengan 120 dan hasilnya adalah 2/3 kali 10 pangkat min 4 atau 0,0000667 mol per mol kali second pangkat min 1. Gitu, sir.
Okay, thank you Muhammad Fauki. Very good. Okay, you got the answer correct. Okay, so I don't have to actually share my answer because that's exactly what I have. All right, so I hope everyone else can understand, and thank you Kevin and Fauki for answering. Okay, those who did not answer, you will have another chance later to answer. All right, so let's go into today's lesson. All right, okay, I hope you understood. Okay, let me just so today's lesson, we will be sharing what you call going further into learning about rate law, right? Okay, so in the previous lessons, we have actually looked at how does your concentration of your reactants and your products and individually how they behave, throughout a reaction, all right? Okay, and also we have learned how the stoichiometry of the reaction is important in order for you to calculate your rate of reaction and so on, especially when it comes to individual species in a reaction. Okay, so today onwards, we will be looking at rate law. Okay, basically how you're going to relate the rate of reactions, right, to the concentration of your reactants. Okay, so here what you want to do is you want to know how the overall reaction, right, and you want to write an expression to explain the overall reaction. So that is the rate law. Okay, so it is basically to relate the reaction to the concentration of the reactant. And because earlier on, all right, we have learned rate of reaction. So here, in order to write out the rate law expression, you will write rate of reaction equals to the rate equals to K, which is the rate constant, times by the concentration of your reactant. Okay, now here we are introduced to a new term, which is rate constant. All right, so in when you write the expression for rate law, the rate constant becomes very important, and later we will also look at how we are going to find the unit of the rate constant. Okay, so your rate constant is actually independent of the concentration because it is a constant in the reaction. All right, but it is dependent on the temperature. Okay, so the rate law of the reaction are experimentally determined equation. Okay, so this expression of rate law or rate equation, they are experimentally determined. Okay, you need to carry out certain experiment in order to determine, and then only you can calculate your rate constant. So that is what we will be learning in the following 4 lessons, where we will learn the different types or different ways you can use to calculate or come up with your rate law or rate equation. All right. So rate law is basically a function of the concentration of the species. Okay, in this instance, it will be the reactant species that are present in your chemical equation. Okay, say for example, you have A, B, C, and so on. Right. So it's a function of the concentrations. All right. So if you remember back in our previous lessons, we have learned that, you know, if it is in the form of gas phase reactions, so of course you will need to use partial pressures, right? So how do you relate concentration to partial pressures? Okay, you can go back to PV equals to nRT, right? Give me a second, yeah. Okay. Okay. So your PV equals to nRT, correct? So your P is equals to N over V RT. Okay, so your pressure P becomes M. This is equal sign, not minus. M R T. Why? Because your N equals to MV. Right? So your big M is equals to N over V. Okay, so you just replace and you will get this expression, okay, which is this expression here. Okay, all right. So simple. It's not a very difficult thing to do. It's also similar to whatever that we have studied in the previous lessons. All right. Okay. So then you can have your rate of reaction as a function of partial pressure when it involves gas phase reactions. Okay. So you need to know the when you are using concentration and when you're using partial pressure. Okay, so your rate law, as we said earlier, it is determined experimentally. Okay, you cannot just infer it from a chemical equation. All right, so just to give you a very complicated example, just to show you. All right, in this example here, H2 in gas form plus with your bromine in gas form to get 2 HBr gas. All right. However, right, the rate law equation for this particular reaction is very complicated. Okay, but you can see here, although the reaction is very simple, but the rate law is complicated. So in order to arrive at a rate law which is as complicated as this, you actually have to do it experimentally. It's not like your rate of reaction, you can straight away, you know, take it as face value from your reaction chemical equation. Okay, but sometimes, right, although it doesn't happen always, sometimes in some cases it can reflect on the stoichiometry. But remember, when that happens, it's because of coincidence or due to the reaction mechanism. So from here, what we need to know, what is important is, all right, your rate law is actually a guide to your reaction mechanism. So this is what we've been saying from the start. Okay, because why you need to learn chemical kinetics, because eventually it can help you to decipher the mechanism of your reaction. Okay, so there are many ways to do it. All right, and you can you know, use empirical methods and so on. So which we will be looking at one by one. Okay, there is initial rate method, there is comparison isolation method, you know, there is graphical method, and then we will be looking at integrals. All right, so that is to just to give you you know, a heads up in the coming weeks. You might want to relook at how do you do integrals, okay, because we will need to learn that in order for you to solve certain of the questions, right? So it can be a qualitative interpretation of concentration versus a time graph, right? It can be a linear relationship from integrated rate laws and so on, right? So the reaction can be simple, but you can have many ways to determine, all right? So your final, in your questions and so on, usually it will be mentioned, okay, use the initial rate method or so on, or use a graphical method. Okay, so later on we will go into more details on the methods. Okay, so your rate law, let's say for this reaction A plus B to get the products, it can be written as rate equals to K, which is your rate constant, A, which is your reactant, to the power of alpha, all right, times the concentration of B to the power of beta. Okay, so this is how you will write out your rate law or rate equation expression. Okay, so if you are asked to write the rate equation for this chemical reaction, so this is the general way of writing. Okay, then you have to use the information given in the question to determine your K, which is your rate constant, your alpha, as well as your beta. Okay, so your K, your rate constant, your alpha and beta, they are experimentally determined, right? So you need a set of experiment. You need to carry out an experiment in order to determine these values, right? So your alpha is normally known as the order of reaction with respect to concentration of A. Okay, so A can be any reactant, right? So the order of reaction with respect to A, okay? And beta will be the order of reaction with respect to B, okay? So when you take your alpha and you plus with beta, you get the overall reaction order or the total order of reaction, okay? So you will know from there, okay, later on, you will see that why the order of reaction is important, right? Because the order of reaction can eventually tell you how the graph looks like. Okay, when you already understand the order of reaction and also you relate to the graphs later on when we do the graphical method, when you look at the graph, you already know what order is the reaction. Okay, so that is why we say when you learn rate law, you can actually determine the mechanism of your reaction. Okay, so your K is the rate constant for the reaction. Okay, so your rate constant, you will see later, all right, that the unit of your rate constant is actually very important. Okay, so the units of your rate constant is very important. Okay, so your rate law usually can appear in this form. All right, so as you can see here, let me just annotate for you. Okay, so your rate law, it can appear in this form, right? So pay attention to this, right? So you can have a zero order rate law. Okay, zero order means none of the concentration of the reactants matter. Okay, so when that happens, your or the order of your reactants are zero. So when the order of the reactants are zero, so you're only left with K. So rate is equals to K. So the unit of your K or your rate constant will be same as the unit of your rate. Okay, so your rate unit is always the same. Okay, your unit for the rate is always the same, which is M as -1. Okay, so that one you already learned previously, right? So now, what happens if it is a first order respect to A? So when it is only first order with respect to A, so that means here, the number here is 1. Okay, so 1 means that you don't have to write. Okay, so the concentration power of 1, so you don't need to write. Okay, so when that happens, all right, then you have to solve your rate equals to K concentration of A. So A concentration is big M, correct? So your rate is M as -1. So that means you can cancel out the M, correct? Okay. So this one is MS negative 1 equals to K. Okay. Concentration is big M. Correct? So your M here and your M here can be cancelled. So your K is equals to S negative 1. Okay, so you can do the same actually for second order reaction and third order reaction. Okay, and you can solve to get this. Right? So you must remember actually the units for K for zero order will be this. Okay, will be this. For first order will be this. Okay, second order will be this. And your third order is this. Okay, you can either remember them or you can, when you're given the question, you can also derive them. Okay, so later we will do a simple exercise to derive. All right, so for now, let's just take it as, all right, so if your second order, okay, let's say only your reactant A is important. So second order with respect to A, so it will be power of 2. Okay, so when that happens, it becomes a second order overall reaction. Okay, remember we said the order, total order is actually you need to plus the 2 exponents, all right, or whichever exponents that are available in your rate law. Okay, so for here, for example, it is first order with respect to A and first order with respect to B. So the overall order is 1 plus, sorry. Okay, yeah, sorry, yeah. Okay, 1 plus 1, okay, which is equals to 2. Okay, all right. Let me just clear this. All right. Okay. So the same goes for rate when it is third order. So it's first order with respect to A, first order with respect to B, first order with respect to C. So the overall order will be 1 plus 1 plus 1. So it is third. Okay. Now, moving on, right? So it is not always 1, 2, 3, 4, right? It can also be half. Okay, it can also be half sometimes, right? Okay, so it can also be half sometimes. So when that happens, it is first order with relation to A, half order with relation to B, first order with relation to C. So the overall order will be 1 plus 0.5 plus 1. So it becomes 5/2. So the overall order of reaction is 5.5 order. Okay, so that's what you need to understand. All right. Okay, now when we talk about zero order rate law, okay, so it means that your rate is independent of the concentration of the reactant. Okay, so one example to let you know in what instances, okay, zero order can happen. All right, so usually, like for example, one example, catalytic decomposition of phosphine on a hot tungsten. Okay, so you only have phosphine, and then you do you put it on hot tungsten and you let it decompose. So when that happens, your pH3 or your phosphine can decompose at a constant rate until it becomes almost entirely disappear. Okay, it is no longer there. All right. So in that instance, it becomes that your reactant concentration is no longer affecting the rate. So your rate becomes equals to K constant. Okay, so in this instance, your rate is independent of the concentration of reactant. Okay, so in other instances, your zero order reaction can also occur, okay, when you have heterogeneous reactions. Okay, so for example, you have a heterogeneous reactant, okay, and it depends on how many other reactant is going to saturate the surface. Okay, so when the surface become overly saturated, so the subsequent reaction become very slow. So in that instance, we can call that as a bottleneck. Okay, so when that happens, it also becomes a zero order because the reactant concentration will no longer be affecting the rate of the reaction. Okay, So those are just a few of the examples when zero order can happen in your reaction. Okay, so always remember the units for your rate constant K will actually depend on the overall order of reaction. Okay, and also very important for you to remember, the unit for rate is always ms negative 1, right? But your m, it can be written as mole per liter, okay, or it can be mole, all right, per dm cube, okay, depending on the question or how it is given, right? It also can be cm negative 3 and so on, all right? Okay, so but depending on the question, but the one thing that you must always remember, it is always m as negative 1. So your rate constant will depend on the overall order of reaction. Okay, so here is the example of how you can calculate, all right, or derive your unit for your rate constant. Okay, so this is the first order reaction. Okay, remember I showed you. Okay, so can I give you a few minutes, okay, all right, to show the workings on how to obtain the different units for rate constant of second and third order. Okay, second and third order. All right, can we take 3 minutes? Okay, I give you 3 minutes. Can you quickly try to scribble out, if it is a second order, how will your rate constant derivation can be done? So your second order and third order. Okay, give you 3 minutes, yeah? Quickly get it done. Okay, all right. So when you write out, okay, similarly, yeah, if you do this, right, if you do this for second order or third order, so that means you need to annotate either 2, okay, for second order, or rate equals to, hold on, let me just write properly. Okay, rate equals to K A third order. Okay, so you do exactly same as this, all right, in order for you to obtain. Okay, let me just show you. Okay, when you solve the equation, you will get exactly m negative 1 as negative 1, all right, and m negative 2 as negative 1. Okay, so the method to do it is you use the same method as here, but now you square, or you must be, if second order, then it's power of 2, then if third order, power of 3. Okay, then you just need to solve the corresponding equation in order for you to get the units for your rate constant. I hope you are able to do it, all right? Okay, now let's move on a little bit so that we have a little extra time, because this one, you guys can try it out on your own. And if you are unable to solve it, you can ask me in the group or later on. Maybe you guys can share it. Okay, share your answer in the WhatsApp group that we have. Okay, on how do you solve your K for second order and third order. All right. Okay, and I will tell you if you are right. Okay. All right. So let's move on a little bit, because later we will have one more group work where you will be solving a question. Okay. So move on a little bit so that we can finish up the factual part of the lesson and move on to the calculation of your, how do you use your rate expression in order to calculate. Okay. So decomposition of H2O2 into H2O and O2. All right. This is one example. Okay, we actually used this example in our previous lessons. All right. So the general expression for rate, okay, rate equation. Now, if you remember back the previous lesson, okay, when you want to write a general expression for rate, okay, so you have to consider that your H2O2 is decomposing. Okay, so you have a stoichiometry of 2. All right, so it's negative 1/2 times by dH2O2. All right, the differential in the concentration of H2O2 over time, which will be equal to the differential in the concentration of oxygen, which is your product over time. So because you're forming your oxygen, there is no negative in front, okay, which is also equals to 1/2 of your dH2O dt, right? So this is the general expression for the rate of reaction. However, if you were to experimentally determine the form of rate law or rate equation, then it becomes different. When you talk about rate law or rate equation, we only consider the reactant, right? And you will put a constant. Now, in this instance, for this reaction, it's already told that by experiment, it is a first order with respect to H2O2. So, different experiment, it will be different. But for this particular experiment, the information is already given to you that it is first order with respect to H2O2. When that is being said, you can write out your rate law expression. Okay, so it becomes very important for you to know how to write the rate law expression or the rate equation. Okay. So when you're given the information, it is first order with respect to H2O2. So you can write rate is equals to K, which is your rate constant, and the concentration of your reactant H2O2 with respect, right, to first order. Okay, so first order, as I said earlier, you don't have to write it. Okay, so that is one example. Okay. Now let's look at the second example. Okay. So another example will be the reaction of nitrogen oxide with fluorine to produce nitrile fluoride. Okay, so you can see here 2NO2, okay, plus F2 to get 2NO2F, right? Okay, now, right, you can actually also experimentally determine the form of rate law. Okay, so your your rate law, okay, becomes equals to K, which is your constant, times by concentration of NO2 times by the concentration of F2, which is your two of the reactants in your reaction. Okay, so you are given the information that, right, let me just write this. Okay, you are given the information. It is first order with respect to NO, okay, and first order with respect to F2. Okay, again, if it is first order, usually you don't have to write. Okay, if it is 2 and above, you will later write. Okay, now the overall order will be this one plus this one. Okay, the overall order of this reaction is 2. Okay, and the rate equation, rate law expression for this reaction is rate equals to K, which is your rate constant, times by concentration of NO2 power of 1 times concentration of F2 power of 1. Okay, so that is how you will write the what do you call the rate expression, rate law expression. Okay, all right. Give me 1 second. Let me just drink water. Okay, so from here you can now roughly be able to see the difference between your rate and your rate constant. Okay, so we keep on harping about rate constant, right? Why? Because it is important that you know how to what you call to derive the units for your rate constant. Okay, and also you know the difference when you're asked to write a rate what you call a rate law expression or a rate equation for your reaction. Okay, so but when we talk about rate of reaction, okay, that's what we learned in the previous lessons, okay, the last few weeks. Okay, it's actually the change of concentration with time. Okay, now when we talk about rate constant, okay, it is actually the proportionality constant to relate your reaction rate to the concentration of your reactants. Okay, it is to relate the reaction rate to the concentration of your reactants. Okay, but your rate constant will always remain constant because as we said, it is a constant, all right? So regardless of what is your initial concentration, okay, your rate constant will be the same because it is dividing the rate of reaction with the reactant concentration. So at any point of time, the rate constant K, the value will be the same, all right, in that particular reaction, okay, or experiment, all right. So for zero order, it's very important for you to remember that the rate and rate constant actually has same units, right? So these are the some of the information from the last few slides that we have looked at that you must remember. Okay. Now, so let's go into a question. All right. So try to pay attention because after this question, you will be broken into your groups. Okay. You will go into your groups and you will try to solve the next question. Right. But I will teach you first how to do it. All right. And when you go break into your groups, I need you to write out the answers or type out the answers in what do you call in a Word document or so on, and you prepare it, and I will come and check group by group, and we will discuss in the smaller groups so that I know you understand whatever that I've been talking about for the last 1 hour. All right, okay. So let us just go through this particular question first. Then we can try the question on group, page 14 in group. Okay, so let's look at this question. All right. Okay. S2O8, 2 negative plus 2I negative to get 2SO4, 2 negative plus I2. Okay, so the above reaction is first order with respect to S2O8, 2 negative ions and I negative ions. Okay, so this is given in your question. Okay, so what you need to know, the first question is write the rate equation for the reaction. Okay, so this is how usually the questions will be. They will ask you to write the rate equation and what is the overall order. Okay, so you must know rate equation. Now we are relating to the rate law, the expression of your rate law. Okay, so let's try to solve the first part. Okay, and your rate is equals to K, okay, which is your constant, and you've been told that, okay, you've been told that this is first order and first order. Okay, so this is the expression of the rate. Okay, as I said earlier, you don't have to write. If it is 1, you don't have to write. So this is answering the first part of A. where they ask you to write the rate equation for the reaction. Okay, by now you must have realized I keep emphasizing rate expression. Okay, because you must know how to differentiate rate equation or expression, okay, as compared to rate of reaction that we learned, right? What we learned previously is only the rate of reaction. Now we want to compare the rate of reaction with the overall concentration of your reactants, right? So here you have your rate constant, then your S2O8 2 negative to the order of 1 and I negative to the order of 1. So the overall order you will write as 1 plus 1 equals to 2, which is the second order. Okay, so the overall order is, this is the second part of the question, the overall order is second order. Okay, all right. Okay, now let's go to B. What is the unit for the rate constant K? Okay, so remember I asked you just now, can you solve the what do you call the unit for your constant? So this actually can come out in your test or your exam and so on. You can be asked to solve just the units of your rate constant, right? So you must be well versed on how to do this, right? Okay, so actually it's very simple, all right? So as we said earlier, right? Just now I did mention to you, your rate unit is always the same. Okay, it is always the same. It's concentration per second. Okay, so mole per dm cube per second. All right. The concentration is mole per dm cube. Okay, so the concentration of S2O8 2 negative is mole per dm cube. The concentration of I negative is mole per dm cube. So if you solve this equation, you will get mole per dm cube per second. All right. Okay, can right? It's quite simple. So you can see here, you can actually cut one of these and you cut this, all right? And then you will be left with mole per dm cube per second, all right? Okay, now, C. At a particular concentration of S2O8 2 negative and I negative, the rate of reaction is X mole per dm cube per second. Right, and determine the new rate in terms of X if the following changes are made at constant temperature. Right, so now they are telling you that the rate of reaction is X, okay, and they want to find the new rate in terms of X if they make the following changes. That means they want to increase the concentration of S2O8 2 negative to be double. Okay, so assume that the initial concentration of S2O8 2 negative and I are A and B moles respectively. Okay, and you are given that your rate of reaction is X. Okay, so put this information into your rate law equation. X is equals to K, concentration of A times concentration of B. Now, if the new concentration is 2A for S2O8 2 negative, so if this becomes 2A, then you can solve here to become 2X. Okay, so your rate becomes 2X. All right, okay, because X is K A times B. So this one, you can replace it with X. Okay, so it becomes 2X. All right. So the second one, what if the concentration of your I negative is half? Okay, so the new concentration of I negative is now half B. All right. So when that happens, you write again, rate equals to K, concentration of A times by half concentration of B. All right. So you bring your half K out, right? Then you're left with, this is X. Okay, simple, right? So the last one, okay, the last one, the concentration of both S2O8 2 negative and I negative are both double, All right. So the new concentration is 2A and 2B. Okay, so when you write that, you have 4. Again, KAB, this becomes X. Okay, so it becomes 4X. Okay, I think that is very simple, okay, for everyone to understand, right? So we can try question number on page 14. Okay, in order to do that, I need you to get into your groups, all right? Dr. Galu, if I can ask for your help.
So we will have how many breakout rooms, Doctor?
As usual.
Okay, 10 ya. Okay.
10 and first 5 for our students.
Yes. Ya, jadi kita akan membagi breakout rooms, breakout room nomor 1 sampai 5 untuk registered students, lalu yang nomor 6 sampai 10 untuk selain dari itu ya.
Okay, so when you have got into your groups, you can start to answer the question and I will enter in to guide you on how to answer.
Ya, room sudah dibuka, silakan masuk, boleh pilih ya, boleh pilih tapi dengan aturan tadi. Jadi 1 sampai 5 untuk mahasiswa yang terdaftar di mata kuliah ini melalui spot, sementara yang lainnya itu untuk yang 6 sampai 10. Tolong pada saat memilih grup dilihat juga jumlahnya ya, jangan sampai terlalu banyak begitu di satu ruangan. Ini room 3 ini banyak sekali ya.
I have to move.
Yeah, Doctor, I think we need to move some people from room 4 to room 2 or 1.
I'm moving now.
So is room 10, Dr. Galuh.
Room 10, kenapa room 10 juga full ya?
Yep, room 10 and room 8 actually.
I think rooms 6 and above.
Room 7 is empty.
Room 6 is empty.
No,
Pak Hafiz, can you also move some people?
But I don't know which one is our student. I'm sorry. I don't have the list.
That's fine. Yeah, okay. I'll try to move. Doctor, I'll try to move people from room 6 to 10. Okay. And probably you can try to
I'm moving
room 1 and 5. Yeah.
I'm moving some of them right now. Room 4, too many students.
Yeah. Okay.
Room 6.
Yeah. Try to move some from room 8 to room 6.
You know this one.
But room 6 is not our registered students, right?
No, yeah. I'm trying to balance the one that the unregistered students because there are also too many in some rooms.
Yeah.
This is for 2 class, right?
It's actually many classes.
No, I mean classes. It's your class and Professor Agus' class, right?
Yes, but I'm not sure if Professor Agus also make it compulsory or only elective.
It would be great. All right. I think this one is one of our student, I believe. Let's move room 7.
Jadi Pak Hafiz kalau mindahin yang 6 sampai 10 yang dibalansin ya, kalau 1 sampai 5 nanti sama sama Dr. Sangi aja.
Oke.
Yang ini aja yang 6, 7, 8, 9, 10 kita.
Oke.
Kalau itu mah bebas siapa aja, jadi nggak usah. Yang penting terdistribusi aja. Asal yang nomor 1 sampai 5 nggak diapa-apain.
Yeah.
Alright. Let's just move this one. Here.
Students are quite quiet, very shy.
Yeah, that's I think it happens. I think some of them has like a confidence in speaking English, because I saw that actually when the last student present, he actually has also finalized the both of the question well, but he just don't want to share. Yeah.
But yeah, I think they have to know it's okay to talk in Bahasa Indonesia, because I can actually understand.
Yes.
Because it's not so much difference. Maybe we can tell them later in the group. They shouldn't be scared. It's okay to make mistake actually. I give them about 5 minutes before I join into the group.
Okay.
To go and see how they are doing.
Ini halo Chandel Sleep, is it a student? Hello Chandel. Halo Vanessa, Vansha, silakan masuk ke room ya. Vanessa dan Vansha ada di situ?
I recognize some of them. So Kinetics is for the second year, right?
Yeah, it's actually for the second year.
It was taken together with gas thermodynamics and phase equilibrium, I believe.
Yeah, it's the same semester.
Yeah, so
Hafiz, do you know Chandel? Chandel is our student?
No, I do not believe so, because at least not in the class of my class of thermodynamics.
Oh, okay. Yeah.
But there are a lot of students from my class of thermodynamics who is in room 10. Is that okay?
Room
so
10. How many people in room 10? Move some of them. Hafiz, move some of them to room 9 and 8.
Okay then.
And then Hafiz, you can also see in room 10 if they already do something, and I will start from room 6, and I think Dr. Sangi will go to room 1 to 5 here, Dr. Sangi.
Yeah. I will in shortly. In a few minutes, I will go in to check on them.
Yeah. Okay.
And I will explain to them in person.
Sure. Yeah. Thank you.
Just give them a bit of time to discuss first.
Yes.
At least if they don't understand or anything, they can ask their friends.
Yeah. Sometimes they don't also get the question. So
correct.
Yeah, we need to.
So let's give them a few minutes to settle down.
I think this should be enough, because in rooms, where is room 9? Oh no. Oh, right.
I think it's fine now, Pak Hafiz. I think it's fine now. So
I will check on
evenly.
room 10.
Okay, thank you. It's quite evenly distributed, so I think it's fine now. Yeah. Vanessa, Vansha, ini kemana ya? Silakan pergi ke ruangan masing-masing. Chandel, Vanessa, Vansha. I hope you guys is not sleeping now.
They
Why you
don't just
here?
they
Yeah, why
don't
you
just
here? You're supposed to
on.
be in the breakout rooms.
Yeah.
Yeah.
I hope they just don't on and then they go and do something else.
Yeah, that's why.
It happens with our students too. So
Yeah. Pansha, Vanessa, di mana ya? Cendol, please go to your breakout rooms now. Doctor, how long can we
uh,
discuss in the breakout rooms? And 20 minutes?
yeah, can that should be fine because I want to go in now to
Yeah,
meet them.
okay.
Yeah.
Okay, thank you.
I'll be joining group 1 now. Okay, thanks, Doctor.
Yeah.
Doctor, I'm sorry, it's still in mute.
Oh, sorry. sorry. I didn't realize I was muted. Okay. So what I was saying is most of you got it right. Okay. And the last question, the answer is rate equals to 8y. All right. And that is all for today's lesson. And we will continue next week on how we're going to determine the order of reaction, all right, through experimental methods and so on. Okay. So thank you. Those groups who have completed your answers, you can upload to the Padlet. Okay, you can write your group names as usual and you can upload to Padlet. All right, good job everyone. Thank you. See you next week.
Selamat
Thank you, Doctor.
ketemu lagi
Thank you,
sama saya
everyone.
setelah dari
Thank you,
kuliahnya
Dr.
Pak
Garo.
Yaya.
Thank you.
Ya,
Thank you,
oke.
Dokter. Terima kasih, Ibu.
Oke,
Ini siapa yang belum
Terima
datang?
kasih semuanya.
Ibu.
Kayaknya masih ada satu orang yang belum datangin.
Bye.
Oh iya. Tadi kayaknya datang pas itu. Ya udah kita tunggu dulu aja ya. Oops.